IOCCC Retro Space Award.
Now, retro as in retrograde, or perhaps? Or?
I just figured it was coming to us from the 60s.
Or a backspace?
Yes, that's true. Backspace, I like that.
Well, I guess what we should do is find out who won the IOCCC Retro Award. So let's bring in the trophy.
And the IOCCC Retro Space Award goes to Cesmoak from the United States.
This is truly a fun, this is really a fun piece of code. And you'll see why it's retro. By the way, you're seeing the source code of Chris's, masterpiece. The red stuff there is the editor, showing, trailing white space. There's reasons for that, but that's the program. And if we look at where it goes, this is the other part of the program right there for that in formatted. So the winning entries have a try.sh script that you can run to see what it does. And so we're starting the try.sh script. And what we see is that first of all, we have this file, primes.dec. And what you see over here, if I can point out this stuff, this is a Fortran program. It's a Fortran 66-like thing. So that gives you a hint as to what might be going on. So we take that Fortran deck and give it to standard input of prog. And what happens is, it runs. It prints the primes up to 100. So we have prog, which is actually interpreting Fortran and actually doing the execution. Now, it's more than just a simple program. Here, for example, is a thing showing you the various logical operators that it can perform, the various Fortran logical operators. And when you run it, they all pass. It's showing you, for example, the various operator precedents of the expressions that are all fully there, and it gives you the correct values. It also has has a number of math intrinsics inside, and those are implemented and run and does what you expect. There's a whole bunch of also format specifiers. So Fortran has some format things that are special, and we see that it actually handles a wide variety of format specifiers. And there's examples of the stuff. From C, people they would do it as spread S, but Fortran hits its sort of format things that are special to it. And of course, there's a whole bunch of control flows, go-tos, and do's, and assigns, and all that stuff there that are, and the try-ifs. It does all that stuff. It works there. As we can see, it all passes and does really good things. Here is a particular example of various sort of quirks of the code, and we see that it actually again works and does correctly. Here is, and what you're seeing at the bottom of a larger Fortran deck, and this is a Fortran deck to look at moon and lunar orbits of the moon, from Earth to Moon, and you see a bunch of stuff about position of the moon and Earth and distances and so forth. So it can do some real sort of computation. But even more so is it has a version where it can actually handle punch card decks, because anyone that does retro Fortran will remember IBM style punch cards. And what we see over here on this side is ASCII graphics versions of what would be punch cards. What do you mean by punch cards? Well, they're like this, right? This is the IBM punch card. The way it works is that the holes represent data. Each vertical column is a character. On the very top of the thing to help humans interpret these, the column of holes is the character that it represents. And of course, Fortran comes in decks that you typically take to sort it, you do a diagonal line. So if you drop them, you can have a chance to put them back, there. But this is what a Fortran deck looks like. Of course, rubber banded to try to minimize the, chance of dropping it. And I say, as a retro, is it, as a kid, as a child, as early as 1964, I remember sitting in front of an IBM 029, card punch, where the blank cards would go into this locker here. You flip that switch and the card would come down. This is where the thing's punched. And so you then go punch. And once the card is done, or you end the card, it flips up into this spot here. And it was hours of endless fun of a kid playing and enjoying, various patterns. There was a very tactile, experience. The card readers look like this. They were much more noisy machines. You put this deck into here in the right way up, and the thing would suck it through and load each card into memory. This particular program, that has been, that Chris did, was emulating an IBM 7040, a very sincere machine with lots of good switches and lights. That's one of those early computers had good blinking lights. This is the blinking light things. And they're the back of the machine, and the core was all nice and wired stuff. So it's a very nice, a machine, very sincere. It's not the fastest machine in the world, but it does do like this. Like there's a Fortran deck to compute part of the Mandelbrot set and then render it as graphics. So it can produce things that takes a little bit of time. Some of the try stuff, actually can take a long time, up to 18 hours, because again, the machine was not fast, there, but it was sincere. Here's another case of rendering the system here. And I will mention, by the way, that I am losing the refresh. I'm seeing it showing up on the site, but my refresh is not showing, in terms of characters. So one of the things that was done by Chris was he gave us the deck for a famous, program. And this program was to compute the space-time curvature around a black hole. So the Minutes 1979 paper was the first thing to do the computation of space-time around a black hole. It was initially published in 1978, revised in 1979. And what happened there? This is the forward thing. This is the reverse set for that. So basically, the printing on paper, and this would produce the negative. If you do the very long computation, you'll get the much more detailed set in here. I unfortunately can't draw on the thing because I've lost my.
Let me.
David, I've lost. Yanni,
yeah,
I've lost the. In just a moment. One moment, please. The next and previous things were working, but the screen is not updating.
Oh.
One moment, please.
Let's try.
Should I try to reload?
I just gave you a new link. There you go. You should have.
Okay.
You should have it.
Let me do this thing. Okay. Okay, I'm bringing this up again for a new window here.
The joys of production.
Yes, I'm sure it's my fault. For here it is, comes into play, and We're back. Yay. Okay. So, I want to point out here. So this is the image that was closely matched figure 11 of his 1979 revised paper. The black hole would have been around here in the screen. And showing you a non-rotating black hole where the stable orbits are 3 times the size. And so this was the first detailed computation done where people began to see that the black hole space warping really warped space quite there and visually gave us our first thing. So it's it was a very important paper, seminal paper that is there. So there is a challenge, by the way, and the fun challenge is you've got this Fortran to see if you can generate an alternate version of the program that will support the Fortran read statement. So, marvelous program.
All right. Is there anything you wanted to add, Leo or Landon, before we move on?
Well, Landon forgot to mention that the program actually parses punch card images rather than Fortran text.
Yes. So you can convert the Fortran text into punch card images and process those punch card entries. Thank you, Leo. Yes, and so it knows that. So it's fully Fortran punch card aware. So congratulations, Chris, for their first IOCCC winning entry.
The IOCCC Who Won Award.
So I wonder who won.
Yeah.
Who won? Who's on first?
I mean,
or
what's
who's
on second? I don't know who's on third. All right, let's bring in the trophy
and see who won.
And the IOCCC Who Won Award goes to Jingpi49 from Taiwan.
So this is a fun program. Here is the source code. You look at one of this TARDIS, the old Doctor Who, please call box thing, which was a prominent, feature within the Doctor Who franchise. It's a telephone free for public use, pull to open, piece of code. And, if you watch what happens when you run the try script, this is what it prints. Okay. I'll advance to the next page. Go ahead.
I was saying that depending on the screen resolution, it displays with the appropriate scaling.
Yes, it does. It does scale to the size there. You probably want to make your window characters, rows and columns big enough to see some of the detail. But if you look, here's the code.
Are you sure that it wasn't Docker?
Formatted. Yes. So here's the formatted version of the code, right? You saw the original one. I'll point out that we've got this, array of some constants there that are important. And of course, there's a main function with some defines up there, and such. There is a fun challenge, and that you saw it ended with the 1963 Doctor Who sequence in ASCII, and it prints Doctor Who towards the end. Your challenge is to produce an alternate version of the program that prints IOCCC 2025. So see if you can produce a version of this program that instead prints IOCCC 25, obviously in block letters preceding. Any other comments? Yeah. And in this program, by the way, you say program with height to give it the size. And we recommend at least 120 characters in height and 30 characters, or 20 characters in at least 120 by 30, to give you a nice clear animation. But it really is, a nice entry. And congratulations to Jing P49 for their first winning entry.